Okay, compound measures again, distance time graphs, and now we're going to introduce some velocity time graphs. Strap yourselves in, ladies and gentlemen. This is where it gets bumpy. Okay, let's have a look. Velocity time graphs. What is a velocity time graph? We've had distance time graphs, where we have distance up one side and we have time along the other axis. This time, guess what? We have time across one axis and velocity on the other. And for the sake of this, we're going to think of velocity as speed, at which point all scientists in the room go, velocity is not speed. But for the sake of what we're doing, we'll think of it as speed. Okay? That should get us through. So we've got basically a speed time graph. So across the bottom we have time, and up the side we have what speed we are doing at that time. So on this graph, at 0 time, this person starts at 6 meters per second. So they're already doing a speed at the start of the graph. Doesn't mean they start 6 meters away. They might start at home. We don't really know. All we know is that they instantaneously start at 6 meters per second. And in fact, at 5 seconds in, they're still doing 6 meters per second. In fact, by the end of the graph, after 10 seconds, they are still doing 6 meters per second. They have a constant speed, which is why it's a straight line going across. Then we could have something like this. There's another velocity time graph. Now, this time, they start at 0. That doesn't mean they start at home. We don't know where they start. But what we do know is they start from standing still. And then they gradually change speed. So after 2 seconds, they are doing about 1.5 meters per second. 6 seconds into the graph, and they are doing just under 5 meters per second. And at the end of the graph, after 10 seconds, they're doing 8 meters per second. They are accelerating. They are changing speed, getting faster and faster and faster as they go. Which is obviously different to, you know, our distance time graph. Okay, which, you know, over here, if I've got a diagonal line here, I start at 2 meters away, and I'm gradually getting further away. But on here, the speed is actually the same. They are just getting further away, but they're getting further away at a constant rate. This one, they are getting faster and faster and faster because it's the velocity that we are plotting. So you do have to be careful with these. Keep in mind what we're actually plotting. Are we plotting what their speed is at a certain point, or like a distance time graph, just how far away they are? And then we might have a velocity time graph like this one. Okay, so they start off at 6 meters per second. We don't know where, but they are doing 6 meters per second. And they're gradually getting faster and faster and faster until they reach 9 meters per second. And then they just keep going at the same speed. So they stopped accelerating, but they're still going at a speed. Doesn't mean they're standing still, they're still going at speed. Then they gradually slow down. Their velocity or their speed is reducing until their velocity or speed is 0. At this point, they are standing still. I don't know where they are, but they are standing still. They could be meters away from me, but they are standing still. Doesn't tell us where they're going, just what speed they are doing. Now this is where it gets maybe a little complicated, so concentrate. You know, if you're trying to look at your phone on YouTube and do this at the same time, now might be a good time to put down YouTube. We have basically 3 things we're going to look at. Distance, so there's my tape measure, and that might be in meters. Speed, which we're going to think of as, you know, quite often something like meters per second. So this is how far I'm going in a certain amount of time. And then, of course, we mentioned acceleration. Now, acceleration means my speed is increasing, or could be decreasing if I've got my foot on the brake. So, and that's meters per second per second. Now, if I've got a distance time graph, I can use that to obviously find out what distance I've gone, but I can also use it to find out the speed. And we found out before, didn't we, in the last video, that if I find the gradient on a distance time graph, I get the speed. Now, here's the thing. If I've got a velocity time graph and I find the gradient, guess what? I find the acceleration. So the gradient on a velocity time graph is acceleration. And this works backwards as well. Now, we don't do acceleration graphs. But if I found the area underneath it, and I'll show you what I mean by that in a minute. If I found the area under the graph, it would actually take me backwards, and I would find out what speed I was doing over that time. Now here's the thing that we're going to have. If we've got a velocity time graph, a speed graph, if I find the area under my graph, I find the distance. So each time, if you think of these things as a sort of progression, distance, then speed, then acceleration. If I find the gradient on each graph, it knocks me up to the next level. So with distance, the gradient finds the speed. If I've got a speed graph and I find the gradient, I get the acceleration. And the area under the graph knocks me back the other way. So from acceleration, I go back to speed. From speed, I go back to distance. So distance, speed, acceleration. Still confused? I bet you are. Now, oh yeah, that's a good point. I've knocked that one out because we don't do acceleration graphs, we can actually ignore that bit, which is going to make things a little bit simpler. So we can ignore that one. So the only area under the graph we're going to find is if we've got a velocity graph. Okay, so that makes things a bit simpler. So on velocity time graphs, we can find the area under the graph. Here's what I mean. Here's the distance time graph. If I find the gradient, so I've got my distance there, so that might be in meters, and I've got my time in seconds. If I find the gradient of that line on a distance time graph, I get the speed because, you know, this bit is distance, that bit's time, distance divided by time is speed. So this will work out the speed, yeah? If I find the, let's say, if I draw a straight line down there, if I find out what area this is, that's utterly useless because it's the wrong type of graph. But let's say I've got a velocity time graph and I find the gradient. So I've got my line there. This is my velocity time graph. I've got my meters per second because that's the difference in meters per second, and I've got my time there. If I divide one by the other, it actually tells me the acceleration. So on a speed graph, a velocity graph, gradient is acceleration. But here's the clever bit. If I find the area under this graph, so all of this, and in this case it's just a triangle, isn't it? So if I find the area of that triangle, that would actually tell me how far I have gone in that time. So the area under the graph can tell me the distance. Basically, find the area under the graph and that will tell you what distance you went. Yeah. For example, where's my little, oh yeah, sorry. I've got a velocity time graph. There we go. My little things have appeared. Calculate the distance travelled in the first 10 seconds of this graph. So between 0 and 10, I want to know the distance. But this is a velocity graph. But that doesn't matter because look, if I've got a velocity graph and I find the area under the graph, it works out the distance. So I just need to work out the area under the line. What shape is it? Yes, it is a rectangle. What is the height of my rectangle? It is 6. What is the length of my rectangle? It is 10. So if I times those two things together, I get 60. And I'm after, what distance have I got? Well, we're working in meters per second, so it's meters. The distance is 60 meters. All I did was find the area under the graph. See, it takes a lot longer to describe than it does to do. It's a lot easier than it sounds. All right, one more example, then I want you to have a quick go. So area under the graph is the distance on a velocity time graph. Has to be a velocity time graph. Here we go again then. So that's time, there's velocity. Calculate the distance travelled in the first 10 seconds of the graph. But the distance, remember, is the area under the graph. So in the first 10 seconds, that's between here and here. So I need to find the area of this shape. This shape is a triangle. And as we all know, the area of a triangle is base times height divided by 2. So what's my height of my triangle? What's between 0 and 8? So that has got a height of 8. So times it by 8. What's my base? Well, that's between 0 and 10, so that's 10 seconds. Well, 10 times 8 is 80. Divided by 2 equals 40. The area is 40, so my distance is 40 meters because that's what my velocity is in meters per second, so it must be meters. Yeah? If find the area under the graph. See, it's not as bad as it sounds, okay? Right, I want you to pause the video. I want you to find the area under these two graphs, please, which will find the distance travelled in that time. So pause the video, find the area under the graph, go. Okay, we've unpaused. Let's find the area under the graph. Now, there are two ways you could do this, because this shape is actually a trapezium. Look, because this side is parallel to this side. So you might have done it as a trapezium, or you might have broken it into two bits and found the area of the triangle and then the area of the rectangle. Okay, both will work. And I'm going to do it both ways. This one, I'm going to break it into two pieces. This one, I'm going to do it as a trapezium. So, but as long as your answers match, that's fine. Now, my rectangle has a height of 2 and a length of 10. 2 times 10 is 20. My triangle has a base of 10 and a height, well, it goes between 2 seconds and 9 seconds, so that's a height of 7. So it's 10 times 7. But remember, this... Oh, no, don't... Oh, there we go. Sorry, my tablet went a bit weird there. Divide by 2, because it's base times height, divide by 2. 10 times 7 is 70. Divide that by 2 is 35. So my distance is those two things put together, because you need that total distance. 20 plus 35 is 55. And we're working in meters per second again, so it's 55 meters. How about if I do this as a trapezium, though? Right, that side is parallel to that. Remember, a trapezium, you add the parallel sides, you times it by the distance between them, that we call the height, and then you halve it. This length here is 6 long, and the bottom of my trapezium is 10 long, so I need to add together 6 plus 10. Well, that's 16. The height, or the distance between my two lines, is also 6, so I'm going to times that by 6, and then I'm going to halve it. And there's nothing wrong with using a calculator at this point, even though I already know that it's 96 divided by 2. 10 plus 6 is 16. Add the parallel sides. Times it by the height. Divide it by 2. I'm right. It is 48. 48. Okay, so the area of that trapezium is 48, and we're working in meters, so it's 48 meters. Yeah? Right. But... oh no, I've got 2 more for you. Yes, right, because I thought you really need to practice this. Now, can I suggest at this point you start breaking things into bits? You could break this into a triangle and 2 rectangles. You could break it into what I'm going to do, which is a trapezium, because that's parallel to that, and a rectangle. Either way, break it into pieces and then find out the area of each piece. This one, I'm going to break into a trapezium, a triangle, and a rectangle. Okay, but you do what you want to do. I'll get rid of those lines so you can concentrate. Pause the video, find the area under the graph, because the area under the graph is the distance. Pause now. We have unpaused the video. Okay, I'm going to break this into... I wish I could draw straight lines to this. Break this into a trapezium and a rectangle. Remember, add the 2 parallel sides. Well, that side is 4, that side is 7. So I'm going to add those 2 together. Then times that by the distance between them. The distance between them, which we call the height, is also 4. So I'm going to times it by 4. And then halve it. So my trapezium has an area of 4 plus 7. Times that by 4. Divided by 2 is 22. Sorry, I'm repeating it because I'm really writing it on my calculator. So that bit is 22. And then my rectangle has a height of 7 and a width of 6. So 7 times by 6 is 42, the answer to Life, the Universe and Everything, if you know who Douglas Adams is. And add those 2 things together and you get 64. So the area under the graph is 64, so it's 64 meters, because my graph is in meters per second. Okay? Oh, right, last one then. Let's do this. Let's go a little bit faster, shall we? Right, I'm going to break this into a trapezium, a rectangle, and a triangle. Now, my rectangle has a width of 4 and a height of 9. So my rectangle has an area of 4 times 9, which is 36. My triangle has a base of 4 and a height of 9. So that's 4 times by 9 divided by 2, base times height divided by 2, which is 18. A trapezium, one side is 6, because these are my parallel sides, aren't they? One parallel side is 6 and the other is 9. So I add those together, add the parallel sides, times it by the distance between them, which is 2, and then halve it, which I already know is going to be 15. And though my distance then is the adding up of all those different parts of the area under the graph. So 36, he says, typing in his calculator, plus 18 plus 15 is 69, the funniest of all the numbers. 69. And we're working in meters, so this is 69 meters. On a velocity time graph, the area under the graph is the distance. Okay? Now, you think now that I'm going to let you go and do a worksheet, don't you? But no, because I'm going to pose another question. And my question is, what if the graph is a curve? Oh yeah, we're going there. Yeah, here we go. Look, there's my graph, and it's a curve. How on earth am I going to find the distance under that now? Right, we use something called, he says, pressing his button, hoping it's going to come up, the Trapezium Rule. And the Trapezium Rule involves finding the areas of trapeziums. Now, the area of a trapezium, as we've said before, is add the parallel sides together, times it by the height, divide by 2. Now, the trapezium rule involves making trapeziums on your graph and finding the area of those. Now, I am going to find, if I break this into too many trapeziums, it's going to be a bit complicated. So I'm going to just break it into 3 trapeziums. Sometimes it says to do these in equal width, sometimes it doesn't. I'm just going to check. I didn't put a thing. No, okay, right, sorry. We're going back. We're going back. There you go. Sorry, back again. Right, there's one trapezium. All I've done is gone, right, my first trapezium is going to be 4 seconds wide. I'm going to draw a line straight up to my graph and draw a line to the start of the trapezium down here. Now, this is actually a triangle, this first one, and quite often they are. If it starts at 0, it's going to start as a triangle. Now, my next trapezium, I'm also going to make 4 seconds wide. So from that point, I'm going to take it up to the graph. Obviously, I'm using a ruler, although on a computer that's going to make no difference at all. And then from my last trapezium, I'm going to draw a line up. Now, notice that this is going to estimate the area under the curve, because I'm going to miss some bits. Look, there's a bit under that curve there I'm going to miss. I'm going to miss a tiny little bit in there as well. But it's going to be a close estimate. And lastly, I've got my last trapezium, because I need to have the area under the whole graph. So at 10 seconds, I'm going to take a line up to my graph, draw a line across there. Now, what I need to know is, what is the height at each of these points? What's my distance? So I'm going to say that is 3.5 meters. And this one is at, oh, it's not 3.5, is it? It's 3.25. It's at a quarter. So let's scribble that out neatly and put 3.25. And this one is, that's 4.5, so that must be 4.75. Usually questions that you get, they'll hopefully give you some nicer numbers to work with. So and then you need to find the area of each of these trapeziums, right? And I'm going to think of them as, these two are definitely trapeziums. This one is a triangle. And it's called the trapezium rule because you break it into these trapeziums with these flat, or diagonal tops, straight tops we'll call them, right? And the height here, of course, is 5. So we find the area of each bit. And my first one is a triangle. My triangle has a height of 3.25. I'm going to times that by the width, which is 4 seconds, and then divide it by 2. And that gives me an answer. And you can put that in a calculator. That's absolutely fine. That is going to be 6.5. So that first bit is 6.5 meters. Let's write it in there. Why not? 6.5 meters. The next one's a trapezium. Now remember, add up your parallel sides. Now my parallel sides are 3.25 because it's the height. It's these things here. These are all parallel, aren't they? Because they've drawn them straight up. The height of that one's 3.25. The height of this one's 4.75. So I'm going to add those two things together and times it by the width between them. Now the width is 4 seconds. And I'm then going to divide it by 2. Sorry, that line was very wobbly. That did make me chuckle. 3.25 plus 4.75 equals 8. Let's times it by 4, divide it by 2, and that covers an area of 16. So this bit is 16 meters. Trapezium rule, because you're just finding the areas of trapeziums. My last trapezium has one side is 4.75 and the other one is 5. Yeah, the two heights of my two sides on my trapezium, just to be clear, it's this that I'm finding the area of, yeah, my trapezium. Times it by the width. Now this one has a smaller width, doesn't it? Which is 2. And then halve it. Add the parallel sides, times by the width, and then halve it. Right, 4.75. This can have a decimal answer, definitely. Plus 5 equals that. Times it by the width there, what we call the height. Bit confusing, isn't it? And then to halve the whole thing, I've got 9.75. Okay, and my total distance travelled, the area under my graph, will be all of those things added together. I know I've written it out like column addition, but I'm actually using my calculator. So we'll add that to 16, add that to 6.5, and we get 32.25 meters. 32.25 meters. This is an estimate of the distance travelled over this graph. Yeah, and that last one was 9.75, wasn't it? And what I did was break it into trapeziums. So we're using the vertical lines on the graph, breaking it into a trapezium. So each trapezium has a straight top. So it's not following completely the curve of the graph. It's got a straight top. So we're estimating what the distance is, what the area under that graph is. Right, I want you to have a go on this one. Now, I know, again, because you can't draw on the graph, it does make it tougher, which is why I've actually drawn on some trapeziums for you. Now, the first one, quite often, as always, first one's a triangle, then you've got a trapezium, then another trapezium, then another trapezium, and then another trapezium. Remember, all of these upright lines, all of these upright lines are the parallel ones. So those are the ones that you need to use as the A and B each time. So we're going to pause it. I'm just going to remind you of how you find the area of a trapezium. Add the parallel sides, so those are going to be, these upright bits. Times it by what we call the height. Now that is the distance between them. And then halve it. And that will find the area of each trapezium. Okay? Right. So pause the video now. It will take you a while. And then find the area under that graph. Good luck. We have unpaused. Right, let's go for this then. Okay, the triangle's the first one, isn't it? And the first thing to do is work out what the height of these. Now, if you've used slightly different numbers, you will get a slightly different answer, but that's fine, as long as you are in the same kind of area of an answer, as long as your method is good. I'd say that was a height of 6.5. That's a height of 9.5. That is a height of, 11.5. And I'd say that one is a height of 13.5. And that, of course, is a height of 15. So we have got 4 trapeziums and 1 triangle to do. So I'm going to try and write small here. So my triangle, first of all, the height is 6.5. The base is 5. We're going to divide that by 2. So base times height, divide by 2 is 16.25. So that first triangle is 16.25. Okay, trapezium 1 then. Does that help if I do that? If I maybe label these things. Add the parallel sides. Now, what are my parallel sides? Well, one of them is 6.5 high. The other one is 9.5 high because these are parallel. Yeah? So 6.5 plus 9.5. And then times it by the distance between them. Well, all of my trapeziums have got a distance, a width here of 5. So the height of each of my trapeziums is 5. 6.5 plus 9.5, times it by the width of 5, then halve it. So that first one, number 1, has an area of 40. So that's 40 meters. Trapezium 2, at this point you might want to, start skipping on. So that's trapezium 2. We have got, 1 is 9.5. Notice how, look, one's, this side here is the tall one on this trapezium, but the short one on this trapezium. So, each side usually gets used twice. And 11.5, those are the two sides of my trapezium. Times them by the distance between them and halve it. So 9.5 plus 11.5, times it by the height there, which is 5, divide it by 2, I get 52.5. Oops, 52.5 meters. Trapezium 3, this does take a long time, doesn't it? Is 17.5. And we're going to add to that 11.5. And then we'll times it by the width of that trapezium is 5, which we confusingly call the height. So 17.5 plus 11.5, doesn't matter which way round you write those really. And then times that by 5, divide it by 2, is 72.5. And let's just put a little line down here because I need to do my fourth trapezium. I'm going to have to tell Alexa to stop beeping at me. Well, hopefully someone else will. That'll be good. All right, my two parallel sides are 15. I did 17.5 for that last one, didn't I? I'm going to have to go back and calculate that. You're all shouting at me again, going, what are you doing? It's not 17.5, it's 13.5. Oh, let's try that again. Right, 13.5 plus 11.5. Times it by the width of 5, divide it by 2. 62.5, not 72.5. You fool. You fool, Mr. Nice. You got it wrong. So 62.5. Right, okay, let's get back on track. So 13.5. It had a width of 5. Yeah, getting the idea now, hopefully? No, says everyone. Times it by 5, divide by 2. And we've got an area of 71.25. Right, okay, so that's the area of each individual one. What I need to do now is add them all up together, just like you did, hopefully. So 62.5, 52.5, 40, and 16.25 all together makes 242.5 meters. Okay, but the main thing is the trapezium rule involves making these trapeziums, so we're estimating the graph because we're not completely following the line of the graph, we're actually missing little bits out, but making a trapezium is a good estimate of it. Yeah? Right. Now, I have put a worksheet here. Now, it might take you a long time to do this, we'll see. Now, the worksheet does have some easy bits like this one. Actually, this question, if you get this question on there, firstly, how many seconds was the acceleration 0? So we're looking for a part of the graph where the acceleration is 0. That's where it's got a flat gradient, so that's going to be their point. Okay, so I've given you that answer there. That's great. Now, whatever time that's at, which is what? However many seconds. You'll have to look at the graph. And it wants to know the distance traveled in the first 15 seconds. Also, the last 15 seconds. So that's between the 25 seconds there and the 10 seconds there. So look, you can see this one is a nice straightforward single trapezium. Don't need to break it up. It's only when you've got a curve, so if you've got a graph that's got a curve, that you need to start breaking it into trapeziums. Okay, so some of them will take longer than others. If it's taking you longer than a lesson would have done, then maybe feel free to do it the next day or message me. Okay, right. That was a lot of talking. Well done. It's a complicated task, but it's one that's got good marks in the exam. Okay, so good luck.